Hello, my name is Faustine Cantalloube, and I'm going to give you a brief overview of climate change, how it affects astronomical observatories. I'm going to focus here on telescopes working in the infrared and visible. So if you take the quality of an astronomical site, so there's the latitude. To access maximum sky coverage, you need to have a clear sky without any pollution, and also stable weather, which means for the visible infrared, cloudless and dry. So Chile is a prime site for that, as an example, but you also need to have access to basic energy to operate the telescopes and resources such as fresh water and food, and also a minimum of social stability. So why can we do climate and astronomy studies now? Because for more than 30 years, astronomical observatories are gathering weather data for functionality. And it means that we can start to have a look at the trends in those data. There's also, since the 90s, some data from satellites, from airports as well, and balloons. And the third item is we also have reanalysis data, so the weather parameters being reconstructed from 1800 to today, as for instance, the ERA 5 reanalysis data from the European structures. At last, we also have climate projections, such as the ones used in the IPCC reports, which are predicting the climate and the weather parameters we will have by 2100. So here is a map of the globe in terms of relative humidity. So you can notice that Chile is in yellow, which means that it's very dry. And indeed, the Very Large Telescope sitting at 2,635 meters altitude has a mean relative humidity of 15%, and it can go as low as 3%. So the first thing you want to look at is the surface temperature. So we know that the surface temperature all over the globe has increased by 1 degree Celsius since the pre-industrial era. The increase is, however, larger over lands than over oceans because the ocean is absorbing the heat. And that's indeed what we see in our data. In red, the institute data, that's the annual median temperature measured at 2 meters above ground. And we can see an increase by 1.5 degrees Celsius since the build of the telescope. And when we check that with the blue data, so the reanalysis data, ERA 5, we can see the same trend. So there is an offset due to the altitude that is not taken into account in our study. If we look at the projections under the worst case scenario as defined by IPCC, the so-called SSP5 8.5 scenario, we would gain 4 degrees Celsius by 2100. So recently, Julia Zeidel, she updated this study, and she made a deeper study, and she shows the same, that she finds an increase of 2% per decade of temperature at sunset at the Parnell Observatory being above 16 degrees. And she also linked it with the El Niño Southern Oscillation and the Pacifical Decadal Oscillation. Another very important piece of work is the work of Caroline Hasselbacher in 2022. She used the Primavera projections that are downscaled from bigger projections, so it's a better spatial resolution. However, it's only until 2050. So here you see the temperature as a function of time. So the black line is the ESO in situ data, so the same as I just showed before. The ERA 5 data, this time without the offset, so it's matching perfect. And in blue and orange, you have the Primavera projections in 2 cases, taking only into account the atmosphere, and in orange, coupling the atmosphere and the oceans. So you can see here plus 0.5 degrees Celsius per decade until 2050. Hotter and drier means that there is more probability of having wildfires. So if you look in the US, for instance, the number of wildfires remain the same. However, if you look at their duration, their intensity, and the damages they involved, you see that it's increasing quite significantly. And indeed, we can see that it's a threat to observatories such as Mount Stromlo in 2003, Siding Spring site in Australia, 2013 has been 2/3 destroyed by the bushfire. Mount Wilson's been threatened in 2020. The Mount Graham's been threatened many times in 96, 2004, 2017, and 21. And at last, those images from the Lick Observatory a few years back. Another picture that is very interesting is the Allen Telescope Array from the SETI Observatory, the Search for Extraterrestrial Intelligence by Alexander Pollack. You can see here the cloud of ash and how the sunlight is scattered in the red because of the presence of the ashes. And if you look at the Fry Fire plume over California, so this same fire, the red pin is the location of the Allen Telescope Array. And 1,000 kilometers from where the Fry Fire took place in Utah, the International Dark Association had this natural reserve, and they made some measurements, and they saw that the PM 2.5 concentration was multiplied by 10, which also meant that the sky background was multiplied by 23 in terms of brightness. So if you look at the telluric lines, so you can see first shape is the black body spectra, just due to the Earth's own thermal emission. And you also see a bunch of lines, which is the absorption features of the atmosphere. So it's mainly the water vapor that is driving it. It's highly variable. And as an example here, you have two images of the same star at 2.2 microns and at 3.8 microns. And in the L' band on the right, you can see the huge background popping up. So humidity is a major feature in astronomy. So we know that the global humidity will increase and the climate change. However, locally, it's very difficult to assess. Here you have an image of Parnell, and there are so-called atmospheric river events, which happens twice a year for about 2-3 days. It actually stems from the Amazonian clouds of air charged with water that are being brought to the Atacama Desert. So there are several ways of assessing humidity, but we usually use astronomers' relative humidity and precipitated water vapor. So as a reminder, the hotter, the more water vapor you can contain in air, pure air. So we did not find any detectable trend from the data we had, and it's been we know that humidity can also bring to leaching, corrosion, and it's dangerous in case of high voltage components. And of course, you cannot open the dome of the telescope if it's too humid. So Julia Zeidel, in her recent study, she found exactly the same. She does not find any clear trend from the institute data. And about the projections by Caroline Eiselbacher, you can see the same data here. There's a slight increase, but it's not very significant. So again, not really conclusion. So we can also look at the turbulence, the optical turbulence, the atmospheric turbulence that is quantified by the seeing. So in that curve here, you can see the seeing as a function of time is slightly increasing. However, the blocks of colors when the Parnell mount was shoveled and the UTs were built and so on. So we have no clue what is what, where it comes from. And Julia Zeidel, she did the same study and she found she had the same conclusion. So there is no increase that is discernible in terms of seeing. And the projections of Primavera made by Caroline also showing the same. There is no increase by 2050. So in terms of seeing from the ground, it might not be an issue. However, if you look at the atmospheric turbulence that is triggered by the presence of the jet stream, so you can see here the yellow label is where the Parnell Observatory is, and this is a wind map. You can see in purple some very high-speed winds. So the jet stream, this layer at 12 kilometers altitude, going really, really fast. We studied this one, and again, we did not find any specific increase, so maybe a little one, but it's very hard to say. And the same IPCC studies showing that we might have a poleward increase and oscillation increase, but it's quite difficult to study because there are so many interactions in that system. So Caroline Eiselbacher also looked at the wind speed turbulence driven, and she also did not find any significant increase by 2050. However, talking about the jet stream, I just wanted to show here, there's one thing that I've learned is that apparently the Northern Hemisphere jet stream is protecting the Hawaiian Islands to be hit by cyclones. So a change in this might increase, obviously, the threatened, how the Hawaiian Island might be threatened by the storms. So here you have, again, the number of tornadoes as before in the US. it's relatively the same, however, the intensity on the right is becoming bigger and bigger. So as a conclusion, I just wanted to drop here that astronomy and climate change is not only those quantities, the seeing the temperature, the humidity, but it's a whole ecosystem. So we also need traveling, we need to record data and transfer them and store them somewhere. We need a lot of energy to operate the telescopes. Pandemic, protests, and safety issues might stop astronomers for doing observations. And of course, you need the basic freshwater, food, and basic healthcare. So with that, I just wanted to say that we need to have an holistic view of the crisis, but also of the solution. What do we want to do in astrophysics, and especially in the academic sector, which is very demanding. You'll find here a few resources. So the 4 main papers on climate change and astronomy. The second one I haven't mentioned is written by Mike Van Kooten and it's focusing on Mauna Kea. It's a very interesting study. So with that, I would like to thank you, and I'm looking forward to discussing with you later.